Okay, so we will look at somewhat more involved proof. The problem which we are going to discuss is called directed Hamiltonian path. Okay. So let us try to see what this problem is. Suppose you have a graph where you put edges, you put directions on the edges, something like this. What is a Hamiltonian path on this graph? So if I put can I visit every vertex? Okay. So this is known as a, so suppose I start with this vertex, visit every vertex and come back to the starting vertex. It's called a Hamiltonian cycle. You have seen this, right? Which lecture? NSN. Okay. So now I am going to put a variant of this and say that, okay, if I put a start vertex somewhere, right, I say that this is my start vertex and this is my end vertex. Okay, I am saying that, okay, can I get a path starting from the vertex S, reaching out every vertex, visiting every vertex exactly once, and finally end up at vertex T. So this is known as a directed Hamiltonian path problem. Okay. So can we given a graph and a start vertex, so what is the problem specification? So given what? Given input, a graph G and vertices S T in the vertex set of G. What are we looking for? What is output? Output is always 0, right? For any decision problem, 0 or 1. What is the requirement? To decide whether so the problem is so instead of writing input, output, etc., input, output, etc. makes sense to algorithm. If you are writing an algorithm, of course, algorithm has to return output 0 or 1. But so the problem is to decide whether G contains okay. So this graph is a directed graph. This is important. The graph which we are talking about is a directed graph. That means an edge can be traversed only along a particular direction. Directed graph. I want to check whether the graph contains a Hamiltonian path S to T. That means a path which starts from S, visits every vertex exactly once, and end up in T. Is this very clear? Okay. So I am not going to write it down the problem formally because I assume that we have seen Hamiltonian. So what are we supposed to? So I want to show that this problem. So our objective is to show that So this is called directed Hamiltonian path problem, DHP. Objective is to show that DHP is NP hard, or objective is to show that DHP is NP hard, and I leave it as an exercise. Show that what should be a certificate to the verifier? The path, right? Once given a path, it's easy to verify whether this actually satisfies the constraint requirements of a directed Hamiltonian ST path. So the hard part is to show that this is NP hard. Now we are going to, so to show that a problem is NP hard, what should we do? So take a non-NP hard problem and reduce to directed Hamiltonian path. So I am going to show that, we will show that so I am going to get a direct reduction from 3SAT to DHP. Again, so for the reduction algorithm, what is the input? So the input to the reduction algorithm, this should be what? A Boolean formula, n and a Boolean formula, phi, right, with n variables. Output, what should be the output? Output of the reduction algorithm from 3SAT to DHP, what should be the output? A graph and a graph, pair of vertices S and T. So S, T, where S and T are vertices in the graph. And what is your requirement specification? So if phi is satisfiable, if and only if, that means if phi is satisfiable, then G should have a directed ST Hamiltonian path, and if G has an ST directed Hamiltonian path, then phi should be satisfiable. So if and only if G has a directed, so output is a directed graph, G is a directed graph with ST or vertices in G, G has a directed Hamiltonian path ST path. Okay. So this is what we are going to do. So this gadget is somewhat involved, but once the basic ideas are clear, it's not very hard to digest what it is. So let's start with the formula and try to see what kind of graph we should construct. Okay. So given, so what I am again doing, as always I am going to do is to explain how to get, take an example and show how to get the corresponding graph. Okay. Given a Boolean formula, how to get the corresponding graph. I will explain the construction. And then of course to get a reduction, that is not enough, we need to get a program to do this, but then once the underlying logic is understood, then it is easy to digest the fact that this construction is easily programmable. Okay. And what one should carefully ensure is that the instance which we create is polynomial on the sized polynomially, the size of the instance which we create at the output of the reduction is bounded polynomially on the size of the input, and the algorithm runs in polynomial time. Okay. So, if you look at the subset sum problems instance which we created, there were large numbers, but still those are all n plus m digit numbers, right. You created a collection of 2n plus 2c numbers, each number being an n plus m digit number. So, that is all polynomially bounded in n and m. Okay, that is just a tangential remark. Let us come back to this. So let us look at this formula phi. Typically, we take a formula in 3 variables, right. So, let us look something like this, x1 and not x2, sorry, or let us look at a formula like this. Okay. So, we are going to create a somewhat lengthy gadget, which but is very easy once the purpose is understood. So, what should we have? We should encode, simulate the formula with some graph in some sense, right. We need to transform the formula satisfiability problem into a graph path problem. And as always I repeat, the reduction does not solve either of the problems, it just transforms, rewrites this problem as the other problem. Okay. So, I need to somehow get a way of expressing this constraint as a graph path constraint, just rewriting this requirement to that requirement on some graph. Okay. So, the way in which we do this is, for each variable I put a lot of vertices and create a gadget. So, I will create a large box. Now, let us order the classes, this is C1, C2, C3. Okay. For each variable I am this is a part of the graph. This box is irrelevant because finally the box will disappear. This is just for thought process. For each variable, the graph has some subgraph will be drawn here. For each variable, some graph will be drawn here. These graphs will be connected with some edges, as we are going to explain. I am going to put a start vertex. So, there are only 3 variables. So, there will be 3 such graphs. Okay. Finally, I should get one graph, but I am going to put edges between these parts and finally will connect these things. Okay. I will put a start vertex here, I will put an end vertex here. Okay. Now, from this I will put an entry vertex here and an exit vertex here. I will put 2 of these, one inside, just like having terminals. Okay. Then, so this from S I can go either to this. Okay. I will also put some vertices here. Let us put something like this. I am not claiming that this is optimal, but the minimum number of vertices, it does the work. So, from starting from S, I can come here, or I can come here and enter this subgraph. Now, from here I can go here, from here also I can go here. Now, the way in which I will draw the graph is such that there will be some number of vertices here. The only way for a Hamiltonian path to start from S and reach T is to either enter this way, go everywhere and come out of this way. So, see, any Hamiltonian ST path should cover all these vertices, right. So, I will put a gadget in such manner. Gadget means a collection of vertices which forms a graph, that is all. So, I will put my graph such that any Hamiltonian ST path must enter this set of vertices from here, either here or here, and then traverse all these vertices in order. It can go out and come back, but there will be some edges going out of the gadget and coming back, that we will worry about later. But you need to traverse all these vertices in this set in order, either this way or this way. After that, you have to come back here, enter this gadget, enter this set of vertices. Now enter from this side or this side, does it matter? Then again visit all these vertices. So if you enter from this side, you have to go out from this side.
But it is not always possible to have a directed path inside the vector graph.
Now let's draw the graph then. That's a plan. See, for example, if I put a graph like this, obviously I can guarantee that if there is a, that's what. This will say that you can only enter from this end and exit from that other end, right? Now if you have something like this way, then again it's guaranteed that if you enter from this side, the only possibilities to visit these vertices is to, there are other possibilities, we will see about that later. Okay. Now the problem is you can enter, go back here and then visit from the other end. These kinds of issues have to be taken care of, but if it is a path, yes, things are simple. Okay. So there is an entry vertex, there is an exit vertex, there is an entry vertex here, there is an exit vertex here. Now from here I can go either this way or I can go this way. From here I can reach this, from here I can reach this and then to T. Okay. Just to avoid, yeah, that's fine. This vertex is superfluous, I can directly put it to T here. Because once, okay, this is your structure so far. Now, okay, so what I have done, I have decided to put some black box for each variable such that this variable graph has 2 entry points which can also act as exit points. Let us see. Now the clauses should appear somewhere, right? I am going to put a vertex for each clause. So here there is a vertex for C1, there is another vertex for C2, there is another vertex for C3. Okay. Still nothing is done. I put 3 vertices for one vertex each for each clause, a set of vertices for each variable. Okay. Nothing has been done so far other than putting these things and drawing some paths. Okay. Then now for each clause, so inside each variable I am going to draw a graph for each clause. Okay. Inside each variable I am going to draw, and this is the final step. So for C1 I will have 2 vertices, for C2 I have 2 vertices, for C3 I have 2 vertices here. I will also put a connector vertex here. Okay. And what am I going to do? I am going to put an edge this way, this way, this way. Again, nothing really deep is happening. Okay. We will do this here also. 2 vertices for C1, 2 vertices for C2, 2 vertices for C3. So in such reductions, the general rule is when in doubt, put an intermediate vertex like this between two gadgets to ensure that the entry and exit is regulated. Certain stories, the plot will be clear only at the end. This is one such. This is it. Okay. So again for each, so what I have constructed so far is a graph where there is a vertex for each class. How many vertices? So if there are 3 vertices in this case, in general if there are k clauses in n variables, if there are k clauses in n variables, so you have something like Ck and n variables. What will be the size of the graph that is constructed? Number of vertices? Well, here 2 into k vertices will be there. Actually, for each class there will be another vertex like this. So you will have 3k plus 1 vertices for each of these. This multiplied by n. So n into some 3k plus something. Okay? Pardon?
3k plus 1.
Okay. For each class, 2k vertices are already here. Then one vertex each is here. Plus one endpoint, I will add one more. So 3k plus 1 inside each of these. Then there are 2 more here for each class. So another 2k you have to add. Okay. So 3k plus 1 plus 2k, yeah, 4k plus 2.
But we do not mention na कि these out-taken vertices are also from close 1 or close 2 or close 3.
No, these are, I just count the number of vertices, nothing more. I am just counting the number of vertices. So the number of vertices comes to something like 3k plus 1 plus 2k, correct? Plus 2, yeah, plus 2 into n plus 2 plus these k, something like this. It's still polynomial because it's still polynomial on the input size, which is k into 3, right? So that's not a problem. Okay. Again, so the graph is not very big, but the graph is not yet done because right now I don't have any connection between the classes and variables, right? I put some vertices, these guys are disconnected. So what I do is, now we start with some work, some thought. So what I do is, I look at this variable. Okay. Now, when I reach, so from here, let me look at, is variable x1 appearing in class C1 or not? This is the question I will ask when at this point, as well as this point. Okay. So is variable appearing in class C1? Yes, variable is appearing in class C1. Okay. So now the next question is x1 appearing or x1 bar appearing, because I don't have separate boxes for x1 and x1 bar, right? So I should worry about whether x1 is appearing, x1 bar appearing. Okay. My convention is, if x1 is appearing, I will arrange things such that from x1's left. So think of this, if x1 is equal to true, there is a corresponding direction left to right. If x1 is false, I keep in mind a corresponding direction right to right. Now, right now this doesn't make any sense because what is x1 is true and left to right, what is the connection? But just keep this in mind. True, left to right. For each variable, true means left to right path, false means right to left path. After all, we are trying to build some correspondence between these, right? What this connection is not clear. We will worry about it later. What I do is, yes, you had some question? You had some question, but you did not tell that. Anyway, so if x1 is appearing in positive form, that means if x1 is appearing, then I put an edge from the left one to C1 and from here to this one. Is this clear? Now, let us look at x1 C2. Is x1 appearing in C2? Yes. In what form? Negated form. So, that I should think of right to left. So, from C2 I put an edge from this side to this and a back edge this way. Okay. Now, x1 C3 let us look at. What is x1 C3 situation? x1 is appearing in negated form. So, I will put an edge from x1 to C3 and this. Is this connection clear? Now, what I do is I start with x2. So, from x2 appears in C1 in what form? Negated form. Yes. x1 appears in C2 in negated form. So, I put a arrow from the right to C2 and C2 back to the left. Whereas x1 appears in positive form in C1, therefore from the left of this x1 C1's left, I put an edge here and edge back to the right. That is my convention. All right. Okay. So, now x2 C1, let us look at x2 appears in C1 in the negated form. So, what should I do? So, this x1's x2 C1's right to C1 I should have an edge and come back to the left. This is my edge directions. Let us look at x2 C2. What is a form? Positive, right? x2 appears in positive form in C2. Therefore, I put, yeah, so from the left of this, I put an edge to C2 and this way, all right. And then let us look at x1 C3, x2 C3. x2 appears in the negated form in C3. So, what will I do? So, right to left, I will put an edge to C3 this way and this. So, this takes care of x2. Now, what should we do? Take x3. From x3, let us look at C1. x3 appears in C1 in negated form. So, I should have an edge from this, oh sorry, so C1, right? That is what this gadget creates. Okay. Then x2 also appears in negated form. So, x3 appears in positive form in C2. So, this is this way, right? And x3 appears in negated form here. So, I will put this and this, yes. So, this finally completes the gadget. We have a wonderful picture. Okay. So, let us look at the easy direction. What is my requirement? So this is first of all, this is a polynomial sized gadget, and all this requirements are all fine, because the number of vertices itself is bounded in polynomial by the size of the input, and therefore you do not have to worry about number of edges, because that is still polynomially bounded on the number of vertices. If a graph has n vertices, how many edges can it have? If it is an undirected graph, it is n choose 2. If it is a directed graph, n choose 2 plus n choose 2 the other way, right? So 2 into n choose 2, which is n into n minus 1, and if you permit self loops, you can have another n edges, it can go up to n square. Okay. All right. So now let us look at the easy part. Suppose the formula is satisfiable. Suppose the formula is satisfiable. What should I show? I should show that there is a Hamiltonian path. Correct. Okay. So what I do is, let us fix, so suppose, assume that x is satisfiable. Okay. By the way, the subset sum reduction as well as this reduction is straight away from this textbook. Introduction to the theory of computation. So this is all textbook material. Better read textbooks rather than listen to lecture notes. Michael Sipser's Introduction to Theory of Computation. There is a chapter of where NP completeness reductions are discussed. I am not sure whether this da is there. All right. So let us think of, so if phi is satisfiable, then phi has a satisfying truth assignment. So in this case, in this example, what can I say? X1, say let us look at a truth assignment. So pick a satisfying truth assignment, okay, and I will pick a variable in each class, a literal in each class which is satisfied by the truth assignment. So before getting to the example, choose the truth assignment and mark a literal in each class that is satisfied by the truth assignment. So this is a very technically correct statement which does not make any sense to anybody. So let us try to fix a truth assignment, do what I am trying to say here. Okay. So let us fix a truth assignment. Give me a truth assignment. X equal to, x1 equal to true, yeah, x2 equal to true, x3, okay, let us fix this truth assignment. Okay. So we fix the truth assignment. Now what I am going to do is tell me one literal from each class which is satisfied. give me one literal from each class which is satisfied. So, in this class, tell me once x1, okay, x1 is satisfied. From this, x2 is satisfied. In this, okay, not x2 is satisfied. Yeah, not x3 is only satisfied, x2 is not satisfied, correct. So, I will pick this. Not x2, yeah. Now, let us see how we can get a Hamiltonian path. Looking at this truth assignment, how to get a Hamiltonian path. Okay. So, I look at x1 is true, right? So, I go to the left of x1. If x1 was false, I would have gone to the right of this. So, my Hamiltonian path will always start from S, cover these vertices, cover these vertices and reach here. The only problem is I need also to cover these guys. Okay. I should visit them exactly once. I should visit every vertex exactly once. So, what I do is, if x1 is equal to true, I enter this way. So, if x1 is true, my entry is this way, because x1 is true. Now, I reach here. I check, I reach here through the left. Before proceeding, I check whether x1 C1 is marked. Yes, x1 is marked in C1. So, what should I do? So, this x1 is supposed to cover this clause, right? x1 equal to true is supposed to, I have taken the x1 equal to true path. Now, this x1 equal to true has been marked here as is supposed to make this clause, see this x1 equal to true is supposed to make this clause true. So, I will go from here, I will take this and cover this and come back here. Okay. So, I take this route to ensure that C1 is covered and come back. Now, x1 has no other job, x1 in your choice of marked these things, x1, see this is nice because x1 has only one duty, x2 is very nicely split. So, x1 is supposed to take care of only one clause, x2 is supposed to take care of another clause, x3 is supposed to take care of another clause. In fact, every clause has somebody to take care of. Why? Because otherwise the formula is not a satisfying truth assignment, right. So, I started with a satisfying truth assignment, therefore, every clause will have some literal who is responsible for making it true marked in the system. Now that I have covered x1, x1 has done its duty, it simply covers the remaining vertices and go out this way and reach here. Okay. Now what should I do? Yeah, now what is the, now I start with x2. What is x2's duty? Cover C2. Now, from which side you should enter x2? x2, because x2 in the positive form covers C2, in the negative form this direction does not cover C2. Okay. So, what you do is you enter x2 from this side, then when you reach C2 you go and visit C2 and come back and go to this end. Okay. And then we enter you reach here. Now you enter x3 from what side? From the right side, because x3 is false. You enter from this side. Only then x3 can cover C3, because x3's edge to C3 is on the right left direction. Is this very clear? So, cover when you reach C3 you go and cover this and come back and continue and reach T. So, we get a directed Hamiltonian path from S to T. So, this is easy. Why should we write so much a big gadget for this? I want to ensure that if there is a path from S to T which is directed Hamiltonian, then I should also get a truth assignment corresponding to it. So, So, the hard part or the more involved reasoning is to guarantee that the only way in which a Hamiltonian path can start from S and reach T in this graph is to first enter this from left or right, then enter this from left or right and cover this, then enter this from left or right, cover this, and somewhere exactly once you have to cover C1, C2, C3 from somewhere. So, this is the only way in which something can happen on this graph. That is what I need to ensure, argue about. Okay. So, can you complete this argument? How can you argue that this graph has, if this graph has a Hamiltonian path, I will also get a corresponding truth assignment. First of all, suppose this graph has a good Hamiltonian path of the kind which we are looking for. That means you enter the left or right, move, will you always get a truth assignment? See, because suppose you enter x1 from the left, suppose you enter x1 from the left. Now, if you visit say C2, then this can happen only if x1 appears in positive form in C2. So, x1 satisfies C2, right. So, if you get a Hamiltonian path looking at the directions of entry and the classes which are covered, you can see that you will get a truth assignment which satisfies the formula. Now, the only problem we should worry about is whether this can have a Hamiltonian path which is not in the standard form. That means a Hamiltonian path, how can a Hamiltonian path be in a non-standard form, not the way which we wanted it to be? You enter, for example, you enter C1 from here and then, or let us say you enter say something from here and go out to something here. That is possible, right? See this, once you enter a clause, something happened. Check. Check, yeah. So, the only way in which things can go wrong is, I enter this clause from say for example here and go out into something else. Okay. So, how can we rule out that possibility? How can we rule out that possibility? So, the argument is the following. If you go out from here, okay, if you take this from the left and reach here, let us say, an argument to right is symmetric. If you reach this node and go out from here, and if you go somewhere else, okay, then your Hamiltonian path has to eventually reach this vertex somewhere, right? Yeah. So, now once you reach here, there is no way of getting out. Even if you reach here, because the only way in which you can get out is either go back here or go back here. Okay. So, this is the argument. Okay. So, if you go from here, now the only way to come back here is from C1. If you do not come back immediately from C1, there is no way to come back here directly from any other edge, right. So, you need to come back somewhere here and come here, but then you do not have a way out of this. You do not have a way out of this. So, the gadget ensures that if you go out from one place, I think the battery needs backup. So, the gadget by construction think I have given the wrong. No, something went wrong. The gadget here is working. Okay. So the construction guarantees that if you go to C1 from or C2, for example, from some place, unless you go back immediately, there is no way to get to this vertex. That's what this construction guarantees. This means the only way in which you can traverse a Hamiltonian path can go in this graph is to go to the left of one place, move to the right, then go to the left or right. The standard form. Yes. So if I keep doing the lecture, then all the recording system will go. So this is for this. Okay. I have one. This is working. Thank you. Okay. So the only way in which you can have a Hamiltonian cycle in this graph, Hamiltonian path from S to T in this graph, is to reach here or here, then take a traversal this way. In the meanwhile, at any point you can go, but you are forced to immediately come back. That's what the gadget ensures. Okay. So the only way in which you can get a Hamiltonian path in this graph is start from this, move either left or right, cover this, then come here, move either left or right, cover this way or this way. So this and finally reach T. That's the only way in which you can reach. And when you are covering this gadget from left to right or right to left, if there is a class which is connected to it, you can go to that class, but you are forced to immediately come back here. Okay. Now if the path is only this way, so given a path of this kind, then it is easy to get a satisfying truth assignment. Why? Because you look at the Hamiltonian path. The Hamiltonian path we have argued should have entered either this way or this way, right? So let's take a different. Let's take a Hamiltonian path in this and try to argue. So give me a Hamiltonian path. You start from S. Suppose I come here. Then which class I can give me a Hamiltonian path. So I should put some vertex numbers, right? So this is 1 1, 1 2, 1 3 and 1 4. This is, let's call this 2 1, this vertex, 2 2, 2 3, 2 4, 3 1, 3 2, 3 3 and 3 4. Let's call these vertices this way. So because if I 2 1, 2 2, 2 3, 2 4, 3 1, 3 2, 3 3, 3 4. Give me a Hamiltonian path in this graph. Okay, you start from S. Which way you go? Okay, so from S I go right. Okay. So as I'll to make this clear, I'll traverse the x1 gadget from the right. Okay. Then yeah, you reach 1 4.
And then from C3, that C3 walks through C3 vertex.
Okay, so from there, you go to C3, so I'll reach 1 4, then cover C3 and come back to 1 3, and then you reach x1's left, and then you enter x2's which way? So x2 you are entering from left, let's say x2 you are entering from left, okay, and then yeah, then you go up to 2 2, Okay.
After that to C2.
I'll go cover C2 and come back to 2, 3, right?
Yes.
Okay.
And then we reach there.
And we reach x2, right? And then I enter x3 from,
Right.
okay, let's say right.
Then come to 3, 2.
Then to 3, 2, yes, and cover
C1.
C1 and then 3, 1 you come back to, right? And then you reach x3 left and finally reach t. So this is a directed Hamiltonian path in the graph. Now what is the truth assignment you get from this?
False to false.
Yeah, you will get x1 right, so false for this. X2 is left, so this is true for x2. And x3 is from the x3 enter from the right? So x3 equal to false. And since every class is visited, see you can visit a class from the right only if it is false in that class. So basically all classes are satisfied by this truth assignment. Correct? You can see that all classes, because x2 true. Now this is a satisfying truth assignment. You can easily verify this. And if you look at the trace the path, you see that when this, for example, here C3 is visited by from x1, which means x1 equal to false will appear in C3. Correct? x1 equal to false appears in C3. That's why C3 is able to cover this. Similarly, you visited C2 from x2 and x2 equal to true should appear in C2. That's why you are able to get this. And you visited x3 from C1 from x3 and from the right side, that's because not x3 is appearing in C1. So you got a satisfying truth assignment from the path. So the path in the graph defines a satisfying truth assignment in the graph, and a truth assignment in the formula. Path in the graph, a Hamiltonian ST path in the graph defines a satisfying truth assignment for the formula, and truth assignment to the formula determines a Hamiltonian path in the graph. So this makes a correspondence between truth assignments in the formula and Hamiltonian paths in the graph. So what is the conclusion? If 3SAT has if this formula has a truth assignment that satisfies it, the graph has a Hamiltonian path, ST path. Now if the graph has a Hamiltonian ST path, then the formula has a truth assignment, so you get a reduction. Is this very clear? Okay. So this is a textbook reduction. Now, once you get one hard problem solved, let's take another problem. Suppose the graph is undirected. That means edges do not have directions. Okay. So I want to show, so I'll define UHP. Given an undirected graph, so we have completed the proof that directed Hamiltonian path is NP hard by reducing from 3SAT, correct? So given an undirected graph, and vertices S, T in view of G, again define Hamiltonian path on undirected graph definitely, right? Does G have an undirected Hamiltonian path. Our Hamiltonian S to T path. So this is the question. So or the language is the set of all G S T such that G has a S T Hamiltonian Suppose you want to prove that this problem is NP hard. I leave it as an exercise again. Show that this problem is an NP. Okay. Now suppose you want to have a reduction from, you want to show that this problem is NP hard. What will you do? Don't one simple intuition one should have is don't start from 3 sat again. Somehow try to get a reduction from already shown problem, hard problem, directed ST Hamiltonian problem to the undirected version. Okay. So you cannot go back and forth. No, there's undirected edges. You have to.
That's why, like, they have both the sense like going forward and going backward.
Yeah. So the idea is for each vertex in the original graph. So okay, let's try to show that. So we claim that directed Hamiltonian path is reducible to undirected Hamiltonian path. So what is the input? Input to reduction? What should be the input to the reduction algorithm? A directed graph, a vertex S and T. Output, an undirected graph, say H, and say let's say 2 vertices alpha beta. So tell me how to get alpha beta from H. So alpha beta is the same as S and T, okay?
Between 2 vertices, you put a backward edge. Like if you have a forward edge, backward edge also.
You cannot put 2 edges between 2 vertices. Now, 2 vertices can have 2 directed edges. But what I am trying to say is that U to V and V to U are not 2 different things now. You are going to produce an undirected graph. No, okay, let's see. So let's see, look at this. If this is your S and this is your T. Now for this graph, what is your new graph? This is your original graph. So G is this, S is this, T is this. What is your new graph? What is your newly constructed graph? H.
Put an extra edge T to this.
See, this S to T, this is an undirected graph. This graph is an undirected graph. Okay, so what are the edges? This is a directed graph. You are going to create an undirected graph. What are the edges there? Just remove the arrow. No, my question is, what is your graph? Then the problem is, if I put this as S and this as T, things fail, right? If I interchange S and T, your reduction fails, because there is a see, this graph has a directed Hamiltonian path from S to T, but no directed Hamiltonian path from T to S. So just replacing the arrows will not work. Pardon? Yeah, that's what is done here, right? Remove the orientation and make parallel edges into a similar. This graph has a directed Hamiltonian path from S to T, but no directed Hamiltonian path from T to S. So suppose this is your graph. Suppose this is your graph. Suppose this is your graph. What is the answer to the directed Hamiltonian path problem? No. If you do it this way, you get yes. That is a problem. That is a problem, because so how to simulate a directed graph with the undirected graph? I will give you a technique. For each vertex, put 3 vertices. See, a directed graph, and there is a notion of an incoming edge and an outgoing edge, right? For an undirected graph, there is no such notion. So what I do is I put 3 vertices for each vertex. There is an in vertex, there is a mid vertex, and an out vertex. Now think about the reduction. Okay. We will do this. Don't think right now. Let's complete the portion and then we will leave the floor open for problem solving. Now, I want to get another reduction. So assuming that undirected Hamiltonian path is solved. So suppose we know that I can define the problem undirected Hamiltonian cycle. What is this? What is this problem? You know what is a Hamiltonian cycle in a graph? Yes. So given a graph, does it have a, now I don't have to specify any start vertex or end vertex because it's a cycle, right? Cycle doesn't have a start or an end. So can you start from one vertex, visit every vertex exactly once and come back to the starting vertex? Now, to show that this problem is NP hard, what is the right problem to start with? Undirected Hamiltonian path. Let's do this reduction. So so what is the problem instance? Or input to a reduction algorithm, what should be a problem instance? What should be a problem instance to this? What should be given? Graph and graph and graph, nothing more. Just a graph. Okay. So a graph, an undirected, and you have to decide yes or no. Okay. So for the reduction algorithm, what is the input? So if I want to reduce, so claim is undirected Hamiltonian path is reducible to undirected Hamiltonian cycle. It's creating problem everywhere. Yeah. So this, how will you show this? Joining S and T creates a problem. For example, suppose you have an edge. Your original graph is a edge. So this is my S, this is an T. How are you going to join them with an edge again?
If they are not adjacent, then use that construction. And if
That's an ad hoc solution. Give me a general way of. You want to add an extra vertex? Do this. Okay. Check whether that works. So try this first and then try to reduce directed Hamiltonian path to undirected Hamiltonian path. So at the end of this, what we have is, we have proved directly that directed Hamiltonian path is NP hard. That we proved in the class. Now the next reduction is to show that undirected Hamiltonian path is reducible, or rather directed Hamiltonian path is reducible to undirected Hamiltonian path. This will show that undirected Hamiltonian path is NP hard. Now undirected Hamiltonian path is now reducible to undirected Hamiltonian cycle. So that will show that undirected Hamiltonian cycle is NP hard. That's where we want to reach. Another exercises show that, what is the remaining problem? Directed Hamiltonian cycle. That I leave as an exercise. That's actually, you can do simple adjustments on the graph, the 3-sat to directed Hamiltonian path reduction. If you adjust a little, you will get directed Hamiltonian cycle. Okay. So I'll leave that problem. So try to do these two reductions. Reduce. So the exercise is to reduce, design reductions for directed Hamiltonian path to undirected Hamiltonian path and undirected Hamiltonian path to undirected Hamiltonian cycle.